Good morning, this is your stats sensei, and we're here today to talk about the chi-square distribution, and we will work a chi-square goodness of fit test. So facts about the chi-square distribution. The curve is non-symmetrical and skewed to the right, all right? So we're gonna have a skewed distribution and skewed to the right. There's a different chi-squared for each degree of freedom. That's kind of like the T distribution. Remember the normal, it didn't matter what there was no degrees of freedom because it didn't, the sample size, regardless what we had, plus or minus 1 was 68%, plus or minus 2 was 95, plus or minus 3 was 99.7. But the T distribution, it varied based on the sample size, just like it will here, but it'll be based on degree of freedom, not the sample size. The test statistic for any test is always greater than or equal to 0. So it's always going to be a positive. We'll always have a positive chi-square. When the degrees of freedom are greater than 90, the chi-square is approximately normal. And because it's skewed, the mean is typically located to the right of the peak. When it's about 90, it gets pretty close to the peak, but it's always to the right of the peak. So I have here 4 different chi-squareds with different degrees of freedom. All right, so in all cases, we kept a p-value of 0.05, but this is a degree of freedom of 1, and we see it's very skewed to the right. When we go to 3, it's a little less skewed to the right. And hold on for a second, I want to try to adjust this image just a bit. Apologize for that. But all of them have p-values of 0.005. And then, and so the 3 were a little less skewed, but still skewed. When we get up to degrees of freedom of 10, we're less skewed, but we're still definitely skewed. And when we get to 90, we're starting to look pretty normal. All right. All of these have p-values greater than 0.05, and that chi-squared would tell you where the rejection zone is. We would have rejected a chi-squared value of 5.99, so about 6. Here we'd reject the chi-squared value of 7.8. Here we reject with a chi-squared of 18.3. And here we would reject if we had a chi-squared of 113. Now, if we look at this, it's hard to tell on this one, but here we'd say, oh, we're probably centered somewhere in this range. Here we're going to be centered somewhere in this range, so about 11, and here we're centered at about 90. So you can see that the center shifts to the right as the chi-squared degrees of freedom increase. Okay, well, technically there are 3 different chi-squared tests, but all 3 of them have exactly the same formula. And this is just a summation, but the observed minus the expected squared over the expected. So observed minus expected squared over the expected. We use the word observed minus expected for residuals when we're talking about regression, but here the chi-squared formula is observed minus expected squared over the expected. The observed values are the actual values. They came from data. The expected value comes from theory, or what we predict or what we believe will happen. N is the number of, N equals the number of data cells or categories, all right? Data cells or categories, and degrees of freedom are number of categories minus 1. This is true. These are only true for the goodness of fit, all right? So this is true for the goodness of fit, which again is categories minus 1, all right? So chi-square goodness of fit. Test to see if a sample distribution matches a known distribution. And we have a list of keywords here. We have the distribution, difference, historical, previous, model, or matches. Any of those are probably a good hint that we're working with a chi-squared. It's not definite, but it's a good hint, suggestion. Chi-squared test of independence. And by the way, these 2 actually run exactly the same, and they're going to look the same. Keywords here are independence, association, or relation. And they are testing one sample with 2 or more variables. Homogeneity, which runs exactly like a chi-square test of independence, and we'll do that in a couple of days, is 2 or more samples, and it's 1 variable. But otherwise, it runs almost exactly the same. Well, it does run exactly the same, but the independence is 1 sample with 2 or more variables. This is 2 samples with 1 variable. Keywords for homogeneity are proportions and ratios. It sounds a lot like a goodness of fit test, but you'll be able to tell the difference once we get to it. All right, so let's look at the chi-square goodness of fit recipe here. Because and by the way, I should tell you this, with the chi-square test, we only can run hypothesis tests. We're not going to have any confidence intervals. So all we'll do is talk about hypothesis tests. So starting off, right or null. Well, the blank data, how we would describe the data follows whatever type of distribution. Historical, previous, uniform, normal, whatever we're expecting. Alternative, whatever our data variable is, does not follow whatever description we had, historical, previous, current, uniform, etc. The conditions, random sample, all right? And to be goodness of fit, it's 1 sample with 1 variable, all right? This is true for goodness of fit, and so I marked that because that's separate for goodness of fit. N is less than 10% of the population. That's going to be true for all of them. And then all expected values must be greater than 5. This will also be true for all the chi-squares. And we're going to have our observed minus expected squared. That's our equation, and we're going to plug in the values. And we're going to have to work on figuring out the expected values. You're going to enter your data into columns L1 and columns L2. The observed, this will be the observed. This will be the expected data into L2. And then you're going to go to the calculator and you're going to go to the stats test, chi-square goodness of fit. And if I go to the calculator and just go there, stat test, chi-square goodness of fit, happens to be letter D on this calculator. So it'll probably be letter D on yours. Our degrees of freedom are N-1. This is true for the goodness of fit, which I'm going to abbreviate GOF. And then we'll state our decision. The p-value is. And our conclusions are much the same as what we've had before. All right. Notice again, we always have to go back to restating the alternative. So our p-value is whatever we calculate. We reject the null. There's sufficient evidence that alpha equal whatever we selected to suggest that the blank data does not follow a whatever distribution we had. So once again, it's a restatement of the alternative. Okay, so here we go. Absenteeism, this is scenario 1. Absenteeism of college students from math classes is a major concern to math instructors because missing class appears to increase the drop rate. 3 statistics instructors wondered whether the absentee rate was the same for every day of the school week. They took a random sample of absent students from 3 of their statistics classes during 1 week of the term. The results of the survey appear in the table. All right, so first off, and they want to, the claim was wondered whether the absentee rate was the same. All right, so does it match? All right, and so the very first thing I did was I sat there and I totaled up all the absentees, okay, and they had 120 absent students, all right, over the course of those 5 days. Well, if it's going to be the same, I'm going to take 120 divided by 5, and I would expect that, you know what, if we're going to have 120 absences, I would expect there to be 24 on Monday, 24 on Tuesday, Wednesday, Thursday, and 24 on Friday. So that's what I would be expecting to happen. It says run appropriate hypothesis tests to answer the professor's question. Well, if they're the same, The absentee data is the same for each day of the week, or if we're intelligent, we can say it follows a uniform distribution, because remember, uniform distribution, everything is exactly the same. So when it's the same, we could say uniform, but you could have written the absentee data is the same for each day of the week. The absentee data does not follow a uniform distribution, would be the alternative, all right? Because the claim was it does. Random sample, not given, but the sample is assumed to be representative of all statistics students. We really always have to have that random sample condition. The expected values are all greater than 5, so I can look at the table, all right? So all the expected values are greater than 5. All observed counts are whole numbers, all right? And that's the third one, saying that, hey, we need to make sure that all the observed counts are whole numbers. And we also need, and I left this out, N is less than 10% of the population, all right? So our sample there's over the course of the year, there's more than 1,200 absences. So that should have been included in there, and I apologize for that not happening. All right, so degrees of freedom. I have 1, 2, 3, 4, 5 categories. Do not count the total as a category. So 1, 2, 3, 4, 5 categories. So my degrees of freedom are 5 minus 1, which is 4. So I have to do write my equation. So I've written my equation and I plug in. Well, 28, my observed, because that's what I observed, minus my expected, 28 minus 24 squared over 24, plus 22 minus 24 squared over 24, 18 minus 24 squared over 24, 20 over 24, 20 minus 24 squared over 24, and then finally Fridays of 32 minus 24 over squared over 24. And we will get to this in just a moment. Now, initially, I'd like you to show all the categories. And if you have just a few categories, you probably should write them all out. But technically, you can go chi squared equals, and ultimately, when we get into longer problems, we will, 24 squared over 24. And we can do the bookend thing that we've done before. And then 32 minus 24 squared over 24. Well, now that I have all the data, I have all of this, I'm going to enter that into my calculator. So I'm going to enter the row 1 into L1, because and it depends on what it is. The expected always needs to go into L2. The observed needs to go into L1, and that's what we said on the recipe. So let's take a look at this. Stat edit, observed in L1, expected in L2. So I have that in there, and I'm going to go stat test, scroll down to letter D, which is chi squared GOF. It's not just the chi squared. I want the chi squared goodness of fit. My observed data is observed was an L1, my expected was an L2, and my degrees of freedom were 5 minus 1, the 5 days of the week, the 5 categories minus 1. And I end up getting 5.667 with a p-value of 0.225. Well, we're not assigned an alpha value, and I just randomly selected 10%. And 0.225 is greater than 0.10. Of course, normally we'd use 0.05 and we'd still be greater than that. But with it being greater, we're going to fail to reject the null. So our p-value is 0.225. We failed to reject the null. There is not sufficient evidence at alpha equal 0.10 to suggest that the distribution of data does not follow the uniform distribution, or to say that the absenteeism is not the and we probably should, the absentee distribution of data does not follow the uniform. Or we could say that the absentee data is not the same for each day of the week. We do not reject the null. Absenteeism follows the uniform and is the same for all days of the week. The next thing is, this showed up on the calculator. We see this thing CNTRB. And this is the contributions. And if I keep scrolling, it's like, okay, oh, 0.6667, then 0.166667, then 1.5, 0.66667, and then 2.6. Well, there happened to be 5 contributions because we actually had 5 of these, all right? And CNTRB stands for contribution. It does not stand for contraband. And these are what they contributed. And if I calculated each individual one, if I just went, take the first one, and I went parenthesis 28 minus 24, close the parenthesis, and squared that, and then divided by 24, sure enough, I get 0.667, all right? So each one of these, that's the value of this. This is the value of that. This will be 1.5, 0.667, and then 2.667. That means this has the largest contribution, all right? And if I sum these up, this plus this plus this plus this plus this, I get 5.67. So for a Friday's absentee data contributes the most, all right? So for the chi-squared goodness of fit, it'll give us that information. And so this has the largest contribution. Now, it doesn't tell you whether it was a positive contribution or a negative. You'd have to look here. 32 is greater than 24, so this has a positive contribution. This 20 minus 24 is negative, so this would have had a negative, all right? But it's still, because we're squaring, we'll have the same thing. All right, so hopefully that helps with this very first one. I highly recommend that you watch the next video as well and get as much practice as possible. We'll actually do 4 scenarios on the chi-squared goodness of fit. And as I mentioned before, there's only hypothesis test for chi-squared. There is no confidence interval. All right, I'll see you in the next one. Thanks for watching.